The current sensor that we're going to use follows this same idea, this same theme, that the motor draws significantly more current, on the order up to an amp, and operates at higher voltages, maybe 12 volts, than the Arduino itself. So we can't directly sense those currents and voltages. We can't reach out with an electrical connection between the motor and the Arduino for the Arduino to know what's going on. And even if we were to design a circuit that maybe made that work, we're just nervous. We're just uncomfortable having our delicate, very power-sensitive electronics, like the Arduino, connected to systems and signals that are just so much bigger that they could very easily blow it up. So we like isolation. The relay that we use this week is an isolation system, so we can control a current much bigger than the Arduino would be happy with. The current sensor is the opposite of that. It's a way to detect a current, again, completely isolated. And it uses some physics, which you don't really have to understand, but it's kind of fun to have a basic idea of what that physics is doing, just so you have some appreciation for how the device works and why it's the right choice. So our current sensor uses something called the Hall effect. It's a fun little bit of physics. And the basic idea is that we're going to drive a current through a piece of material, and the electrons are the current. That material has the property that when you put a magnetic field on it, the electrons bend, their path changes, as you can see there. And if you notice the voltmeter on the top, the voltmeter is connected orthogonal to our current flow, and it can detect when those electrons are being pushed around in the material. You don't really have to understand all the physics of that. The key idea is that our current, represented by the little battery here and the blue electrons flying through the material, is electrically isolated from the voltmeter, because there's this piece of material is not electrically connecting our current and the detected signal, which is the voltage in the other direction. That magnetic field is provided by a fixed magnet built into the little package. When current goes through the material, the magnetic field, which is always there, causes those electrons to bend, and the amount of voltage on the voltmeter depends on the amount of current. So we get a signal, the voltage, that depends on the amount of current going through the material, but the current and the voltmeter are not electrically connected. They're actually separate circuits. Again, that's the key thing we wanted. We can now put boatloads of current through this device, and we can engineer it to give us a voltage which is some nice level that we might like in our Arduino. And there's no chance that that current can get out of its path and into the voltmeter and thus onto our electronics. The two are electrically isolated. So don't really have to understand the physics, but the key idea is that the two systems are separate. We use this weird property of this material and how electrons move in magnetic fields to detect the current is there, but without actually putting an ammeter in the middle of the current stream, because that would connect the current and the sensor itself.